Hi guys, this is Mrs. V, and I'm going to show you a few more examples of transformations of a tangent graph. To start off with, we need to familiarize ourselves with a regular tangent graph, or what I've called a fundamental period of a tangent graph. So the fundamental period of a tangent graph has a vertical asymptote at negative pi over 2 and another vertical asymptote at positive pi over 2. And then we have these important points. We have negative pi over 4, negative 1, 0, 0, and then pi over 4, positive 1. When we talk about any of our transformations, we're always going to talk about transforming these two vertical asymptotes and then these three important points. One thing I want to point out is that this fundamental tangent period from a vertical asymptote to a vertical asymptote does have some symmetry. Halfway through the period, the function is hitting its midline, and then halfway through those halves, or a quarter of the way and 3/4 of the way through the period, so if you think about splitting this period kind of into 4 equal pieces, we're hitting those other two important points, and those are the places where the tangent graph has a slope of 1. Now, of course, those actual slope values will change, or those output values will change as we consider a different function. Whether we're considering a transformation horizontally or vertically, all of those points will change. So let's take a look at this example with this graph of y equals 2 tangent of 2x subtract pi over 4. We should have an idea of what this 2 does from regular sine and cosine functions. This 2 corresponds to a vertical stretch. So it's a vertical stretch. And what that actually means is that we're going to multiply the y values by 2. So we're going to multiply the y values by 2. Now, things on the inside of this function get a little bit more complicated. So I want to think about this 2x subtract pi over 4. What I'm really trying to do with these transformations is find out a new value of x, so I'm going to call that x sub n, that I can plug into this argument. So this argument is this whole entire thing, 2x minus pi over 4. So I want to plug some value of x into that and have that work out to be the same thing as an old value of x that I had from my original tangent function. So if I examine this, I could solve for x sub n. I could add pi over 4 to both sides, so x sub 0 plus pi over 4, and then divide both sides by 2. So x sub n would be the original x plus pi over 4, and then all divided by 2. So really what I'm doing with my x values is I'm adding pi over 4 to the x values, and then I'm dividing that result. Divide that result by 2. So let's go ahead and see what that looks like. I'm going to write down the important points that we have from the tangent function. So our important points are asymptotes. So this isn't actually an important point, it's an asymptote. And then we have negative pi over 4, negative 1, 0, 0, pi over 4, 1, and then my other vertical asymptote. So multiplying the y values by 2 on each one of these is fairly straightforward. So this, I'm just going to fill in the y values. If I multiply each of them by 2, I can figure out what happens. Now those asymptotes were x values, so there's nothing to do with the y value. Okay, but it's a little bit trickier. I'm going to add pi over 4 to the x values and then divide that result by 2. So really what I'm doing is I'm taking these old x values, plugging them in right here for the old x value, and figuring out what the new x value is. So just an example of how that would work for this first point. I could say that my new x is my old x, my old asymptote, negative pi over 2, plus pi over 4, all divided by 2. Well, that works out to be pi over 4 divided by 2, or pi over 8. So my new asymptote is going to be at positive pi over 8. Okay, similarly, I could do that for my other asymptote. Add pi over 4 to that value. So my new asymptote corresponding to pi over 2 would be pi over 2 plus pi over 4 all over 2. This is 3 pi over 4, and then divided by 2 is actually 3 pi over 8. So my new asymptote is going to be at 3 pi over 8. Now, I can do these for the other values, particularly the 0 is easy to do this for. So 0 plus pi over 4 divided by 2 equals, something is not right here, equals pi over 8. I see what it is, and hopefully you caught this and were wondering, what the heck is she doing? This should have been negative pi over 4, and then divided by 2 is negative pi over 8. Okay, so this middle, what was the origin, is now going to be at pi over 8 comma 0, and this should be negative pi over 8. I could fill in the other values, but I'm going to show you that I don't really need to. I'm going to go over to the graph and I'm going to start my asymptotes. So at negative pi over 8 and 3 pi over 8. We need to choose our own scale. I would suggest choosing a scale that allows you to equally divide your period into 4 pieces. So if I made this negative pi over 4, 2 grid marks, then I know exactly where negative pi over 8 is. And if I made this pi over 4 and pi over 2, each one of my tick marks is an eighth. So I can say this is 1 pi over 8, 2 pi over 8, 3 pi over 8. That's where my asymptote goes. Okay, then we know that our origin point ended up actually moving to pi over 8 comma 0. So that's right here. And then from there, I know that my other 2 points are halfway between the distance between the center and the 2 asymptotes. So let's go ahead and do our scale. Let's just make the y value scaled Okay, so now we'll look at a slightly different example. This example has a vertical stretch and a vertical shift. It also has a horizontal shift and a horizontal stretch or compression. The difference is that this argument is in factored form. So I'll write down what the transformations are. I'm just going to pause and put them in there, and then I'll explain what they are. Okay, so what I've written is that I'm going to multiply the y values by 3 and then add 1, divide the x values by 2, then add pi over 4. The multiplying the y values by 3 and then adding 1 should be fairly straightforward. I kind of think of this tangent function as just these are some outputs, some y values from the old function. Regular order of operations would be to multiply first and then add. Now things on the inside aren't quite what they seem because I'm not trying to evaluate, I'm trying to plug a new value of x in here and see how that relates to an old value of x. So really it's like I'm solving this equation, 2 times x subtract pi over 4. Now these are really new x values and I want them to equal old x values. So to solve for the new x values, I'm going to first divide both sides by 2, and then I'm going to add pi over 4 to that. So my new x values are my old x values divided by 2, and then have pi over 4 added to that. So that's exactly what I said over here. So as an example, we could take our first asymptote in a fundamental period of the tangent function. X equals negative pi over 2. This is my old x. The new x that corresponds to that is I have negative pi over 2, and I'm going to actually divide the x value by 2 and then add pi over 4. So dividing it by 2 is really the same thing as multiplying by a half, and then I'm adding pi over 4. So I get negative pi over 4 plus pi over 4, which is 0. So that's my left asymptote. My right asymptote in a fundamental period of tangent would be at pi over 2. So we'll do the same thing, pi over 2. We are going to multiply by a half, then add pi over 4. So I get pi over 4 plus pi over 4, which is pi over 2. So my asymptotes, we know where our asymptotes fall now. Our asymptotes fall at 0 and then pi over 2. I'm going to choose a scale that allows me to split my period into 4 equal pieces, so I will choose a scale so that 4 tick marks actually equals it equals pi over 2. So here's pi over 2, and we know that our asymptotes fall at 0. Isn't this working? There we go. And pi over 2. Now we already know that our midline, if we could call it such a thing, our midline is going to be at 1. If we were to scale our y values by 1, this would be 4 and negative 4. We could go ahead and fill in the midline. So here's our midline. We know that a tangent function, a normal period of a tangent function, falls right on the midline in the center of its period. So we know we're going to fall right here in the center of the period. Okay, then we can start thinking about, well, halfway between that, I'm going to have those important points which were corresponding to negative pi over 4 and pi over 4. Except that when we look at this function, we know that we have a vertical stretch by a factor of 3. So instead of being 1 unit above the midline, they are now going to be 3 units above and below the midline. So when I'm looking at this graph, I'm going to say, well, halfway between the asymptote and the middle of the period, so right here, I'm going to be 3 units below the midline. Oh, that was only 1 unit, 2 units. So 3 units below the midline. Okay, and then halfway between the middle of the period and the end of the period, I'm going to be 3 units above. Okay, and then we just connect that with the shape that we would normally see happening with a tangent graph. And we'll use the trick of, if it doesn't look that great, let's make it thicker. And then it looks beautiful. Still want to draw those arrows. Now my period is pi over 2 in this case because it had the same exact omega or horizontal stretch or compression factor as the previous example, but now the resulting shift is pi over 4. That's where the origin moved to. So kind of the center symmetry point of this graph is now moved pi over 4 units to the right. And then you just repeat this period every pi over 2 beyond that. So now it looks something like this with everything filled in. And then of course I encourage you to check your answers with Desmos. You can set up the scale and everything so it matches your scale and check exact points.